Hey guys, so this week you guys are conducting the lab bromination of cholesterol. So first of all, I'm going to share my screen with you guys. I'll show you. So this molecule here is our cholesterol, if you see my mouse, and we are just brominating it. So it's a very big, intimidating looking molecule, but really we're just focusing on this double bond here, because see, we have this double bond. One side has two carbon substituents and one has a singular carbon substituent. The other is a proton. It's just not labeled because we don't draw in all the protons. And so we are brominating it. This is our bromine on acetic acid. In our MTBE, our methyl, see the CH3, tert-butyl ether, so MTBE. And it's at room temperature, which is 20 degrees Celsius, and we end up with our brominated cholesterol over here. And as you notice, the bromines add opposite to one another, anti to one another. So just to simplify this, I brought up some examples. So here's a pretty straightforward example of what would happen. And here we have cyclohexene with a single methyl coming off of one of the terminal sp3 carbons, sp2. And the bromines, they always add anti. So in this example, they are demonstrating their stereochemistry of the one methyl group that's coming off. And so it can either go, towards you or away from you, but in either case, the other bromine is going to be opposite to whichever direction this bromine on the methyl carbon is attached to. Now, the other reagent they used here is CCl4. You might see that on your exams, but another popular one that you will probably see is FeBr, which is here. So it'll be like HBr, hydrobromic acid, over FeBr3. And that's another reagent for bromination. You'll see, sometimes you'll see this Br2 bromine over HB. That's just HNU. It just stands for UV light, ultraviolet light. And then sometimes, yeah, you'll have hydrobromination, but that's completely different. And I'm sure you've learned about that. If not, then that is another topic for another day. But anyhow, today's procedure, you take 100 milligrams of your cholesterol that is weighed out, that you are going to mass out, supposedly. And to that, we're going to dissolve it in 2 milliliters of your MTBE, your methyl tert-butyl ether that we talked about before. That's going to be our solvent. And then to that, use an automatic pipette to pipette in our bromine. And this bromine is dissolved in a solution of acetic acid. So it's a red solution, so you take up 110 microliters of that, and you're going to add that directly to the Erlenmeyer flask. Now you're going to swirl it on the table on the bench, because the Erlenmeyer flask is actually designed a specific way. So if it's flat on a table, you can swirl it around as fast as you want, and the liquid or any contents inside will never shoot out the top. It's actually designed that way. So as you spin it around and the liquid starts to rise up the sides of the tube, it tapers off so that it actually reaches an asymptote that you just cannot reach that circular velocity on any surface. No human can. So you'll never spill it as long as it's flat on a table. So you're just going to swirl it, and in about 2 to 5 minutes, maybe 10, the reaction's done. You want to make sure you add enough of your bromine on acetic acid so that it remains like a slight yellowy orangey. That means you have a slight excess. If it turns dark red, you have way too much in there, and you're going to have chlorine vaporizing off, and it's going to burn people's eyes and nose, but we don't have to worry about that. But you don't want to add too much excess, just a little bit. If you don't add enough and it's a clear solution, then you're going to have unreacted cholesterol, which we don't want. So anyways, once it's been going and it's slightly yellow for about 2 to 10 minutes, then you can set up your vacuum filtration, which we've gone over before. So we're just going to dump the contents into our vacuum filter, and then we've prepared a solution of 30% MTBE, or solvent, methyl tert-butyl ether, in glacial acetic acid. Now, acetic acid is just the 2-carbon version of acid, so we know what carboxylic acid are. It's the C double bond OH. So formic acid is just a C, the 1 carbon, the central carboxylic carbon, with an H coming off of it, it's formic acid. Acetic acid is just with a methyl coming off. So it's CH3, C, double bond O, OH. That's acetic acid. Now vinegar has acetic acid in it. It is acetic acid, but it's a 5% solution. Now glacial acetic acid is pure acetic acid. It's 95 to 100% acetic acid. It's called glacial because it has a freezing point of 16.6 degrees Celsius. So if it actually, you cool it down in your refrigerator or whatnot, pure glacial acetic acid will freeze into a solid block. So that's why we add the 30% MTBE, so that we mix the solution up and it removes that physical trait. So it will not freeze at 16.6 degrees Celsius. Kind of like with our melting points, if it's impure, the melting point is going to be off. So we impurify the glacial acetic acid to change its melting point. So it will no longer freeze at 16.6. So we can use it to wash our product. Isn't that cool? So anyways, you have 30% MTBE, and the other 70% is glacial acetic acid, the 100%, 95 to 100% acetic acid. And you cool that down on ice because you want it to be cold, because we know our product is more soluble in the room temperature to warm solvent. So we cool it down, we decrease the solubility of our product, and then we drop it over, just dripping it onto our product that's slightly yellowy orangey on the vacuum filter still. And you'll notice that it just washes off that orangey yellow color. And because it's cold, it won't dissolve your pure product. So the white pure product will remain, and just the starting material that's left over, the bromine, that's red and orange, that's red, yellow, and orange, that'll be washed off by the cold 30% MTBE to acetic acid solution. Then you let it dry for a few minutes, then you get it into your tiered aluminum dish, let it sit overnight or for a week, and then you get your weighed results the following week in your melting point. I am going to, so for this lab report, let's see here. Zach, here are the calculations. First of all, let me go over the mechanism real quick. I'm going to share my screen. So it's same deal for the lab report. I'm sure you know what to do or what you're expected to do by now. But as far as the chemistry is involved, this is what I want you to talk about right here, the mechanism. So first of all, there's going to be your trans 2-butene and cis 2-butene. These are two examples of double bonds. So in our cholesterol, we're going to have example of something kind of like your trans 2-butene, except this side has two carbons coming off it and it's locked in that position. Because remember, this is a steroid. So anyways, we're going to go ahead and brominate. But the important thing to remember here is that the bromine is going to be attacked from either the top or the bottom side, it doesn't matter which, of your double bonds. The pi electrons will attack one of the bromines, forcing the electrons onto the other bromine, okay? And now that's a partial bond that's formed. It forms this triangle, this bridged bromonium ion. And now the other bromine has a full -1 charge. And this bromine is splitting its positive charge between these two carbons, and they're sharing their negative charge, that they're now sharing their electrons with this positive bromine. That's why this line is dotted, because it's all partial bonds. It's kind of an intermediate, unstable intermediate that immediately reacts and changes into the product that's right here. One of these two products. These are the two conformer products. So the bromine is attacked by the pi electrons, forms this bridged intermediate, and then the other bromine, your Br minus right here, attacks onto one of these carbons. As you see, here's the bromine. You can go into this carbon, you can go into that carbon, and it forces that other bromine in the bridged bromonium ion intermediate onto the opposite, and they form anti to one another, always. So here's an example of the stick and twig configuration. Here's an example of your Newman projection. And I just want you guys to be able to describe in words what exactly the mechanism that's happening to the cholesterol is. And you don't have to go too much into the Newman projection and the ball and stick, because it is a locked figure. It's a steroid we're talking about. But use the cis-2-butene and the trans-2-butene examples to make it easier for you guys to discuss the mechanism in your reports. As far as the calculation goes, I'm really going to be grading on your discussion of the mechanism and the chemistry, like which side the bromine is attacked by, the reagents used, things like that, as opposed to the calculation, because this calculation is simple. You take cholesterol, you brominate it, use excess bromine, so it's a 1-to-1. You take your 100 milligrams right here of your cholesterol, your starting material, and here's 386.66 milligrams per millimole. It's just upside down right now for the conversion factor. That 386.66 milligrams, that's your molecular weight of your cholesterol. So you're taking your mass and you're timesing it by the inverse of your molecular weight. You're getting the amount of moles, and then that amount of moles is going to be equal to the amount of moles of your product, your brominated cholesterol. So then you take right here, 606.52 milligrams per millimole is the molecular weight of your brominated cholesterol. Times that by the millimoles you're expected to get, and then bam, you get your theoretical yield mass. 158 milligrams, supposed if you started with 100 milligrams of cholesterol, you should get 158 milligrams of brominated cholesterol. Now, I'm just going to let you guys use, so your isolated amount of brominated cholesterol is going to be 120 milligrams. And not the 121 in the example, but 120. I'm going to include it in the email, and I expect you will use that for your calculation. If you have any questions, feel free to email me. I know I haven't been as keeping up with all of my emails from you guys that I get constantly. I've been working really hard in the lab, and so I do apologize, but I'm meaning to pick that back up. We only have a few more weeks left before we're permanently online for the rest of the semester, and then we're getting a bit of a late start. I think January 16th is the date back. So good luck, guys. I'll be posting a review for the final soon. All right. Great talk.